Hey guys, welcome back. We'll continue with the book Python for Data Analysis, and in this video we're going to learn about pandas. If you want to follow along, feel free to subscribe to the channel, and let's jump right in. After covering NumPy in the last video, we are now going to continue with pandas. Panda is a library that contains data structures and data manipulation tools designed to make data cleaning and analysis fast and convenient in Python. If you want to follow along, you can head over to wesmckinney.com/book and read the book for free. We're going to start out with an introduction to pandas data structures. Then we're going to cover the essential panda functionality. And then we're going to cover how to summarize and compute descriptive statistics using pandas. To get started with pandas, we first need to cover two of its most important data structures, which are series and DataFrame. A series is a one-dimensional array-like object containing a sequence of values of the same type and an associated array of data labels, which we call the index. Let's switch into our terminal and activate our conda environment, and then we can open up IPython. Now we can start by importing pandas, and again we're going to use an alias pd in order to save on typing. We can then generate a new series object by calling series on panda and passing a list as an argument to it, and we're going to store that in the variable object. Now if we type in object, we can see that we have our list of values here, but also an index that has been added. We can also see that the data type is of type int64. Now we can take this object and we can get its array representation by calling array on our object, and this is going to give us back a panda array. And this array is only going to contain the values, not the index. If you want to get the index instead, we would simply call index on our object, and this is going to give us back our index. In this case, we have a range index starting from 0 to 4 in steps of 1. Now we can also create a series with an index identifying each data point with a label. For that we can define a new series, but instead of just passing a list of values to it, we can also specify the index. So in this case here we specify strings as an index, D, B, A and C. So if you have a look at our object now, we can indeed see that this is used as the index to reference the values that we provided. And this also becomes clear if we call index on our object too. This again is going to show us the index. This time we don't have a range index since we provided our own index values, and the data type is object. Now we can of course use our index in order to refer to the values. So for instance, we can refer to the value at index A, which gives us back -5, which of course is a value corresponding to our index. And we can also get back the values of multiple indexes at once by separating them by a comma. And this way we're going to get back the respective values. We can also use comparisons in order to filter our series. So here we are looking for any object with a value greater than 0. So we are excluding the negative values. We can also perform mathematical operations, for instance multiplying each value by 2. So in this case each value will be doubled. And we can also check if certain values are in our object. So here we are checking if the index B is in object 2, which will give us back the Boolean value true. We don't have to use lists in order to create new series objects. Instead we can also pass a dictionary. Here for instance we have a dictionary of different cities. Now as before we would call series and pass our argument, in this case the dictionary to it. And if we now have a look at our newly created object, we can see that the keys in our dictionary now corresponds to the index of our series, and the values in our dictionary are now the values in our series object. We can also easily convert a series to a dictionary by simply calling toDict on our series, and this is going to generate a dictionary for us. Now as we saw, by default the keys are going to be used as the index of our series that we're generating. If we want to update that, we could for instance define a new list of states, and then we can create a new object passing our dictionary that we created before and specifying that the index should correspond to the states that we defined. And if we now have a look at our object, we can see that the order is now adjusted and is based on the different state fields we have, and the values are matched accordingly. Now for California here we have a value of NaN, which stands for not a number and means that the values are missing. So if we have a look at our dictionary again, we can see that California was not included in the list of keys, and therefore no value is provided. And we can also easily check in Pandas which entries in our series have a value and which ones don't. We can, for example, use the isNA method, which is part of Pandas, and pass our object 4 here as an argument to it. And this way we can see that California is indeed not available, and for all the other states which are available and have a value, false is returned. If instead we want to do the reverse and check for which values are present, we can instead use a not-NA method, and we can see that for California it returns false because no value exists, and for all the other states true is returned. Now both the series object and its index have a name attribute. So for example, for our object 4 from before, we can set its name to population, and for its index we can set the name to state. And now if you refer to object 4, we can see that state is shown just above our index, and the name is also displayed, so population. So this makes it possible to label our data. Now a series index can be altered in place by assignment. So if we look at our object from before, we can use the index attribute in order to update the index. So rather than using the default index 0 to 3, we can set a different index. And if we look at our object again, we can now see that rather than having the default ranged index, we now added our labels as index values. Data frames are another Panda data structure. A data frame represents a rectangular table of data, which contains an ordered named collection of columns, each of which can be of a different value type. To better understand data frames, let's open up our terminal and let's activate our Conda environment. Then we can switch into IPython. Now we first need to make sure that we import pandas, and again we are going to use the alias PD. And there are many different ways to create a new data frame, but one of the most frequent ones is to use a dictionary, which contains lists of equal lengths or arrays of equal lengths. So here's an example where we have a dictionary that has the keys state, year and pop for population, and then as values we have lists which have the same number of elements. Now in order to turn this into a data frame, we can call DataFrame, which is part of Pandas, and pass our data dictionary as an argument. Now if you have a look at the data frame, we can see that it automatically generated our index, and then we have our table here with 3 different columns, which corresponds to each of the key value pairs in our original dictionary. Now if you use Jupyter notebooks instead, then the data frame will be displayed like such a table here. Now if you have a very long table and we only want to display the first 5 columns, we can go ahead and we can call the head function, and then we can see this would only include the first 5 rows, so from index 0 to index 4. In a similar way, the tail method is going to return the bottom 5 rows, so in this case the entry with index 0 would not be displayed. We can also change the order of the columns and specify that. So for that we would provide a second argument to data frame columns, and here we can specify the order of columns that we want to display. So we can switch this around and have year first, then state, and then population. And this is what we get back. Now if we use the columns attribute and we pass an entry to it that is not contained in our dataset, and we then take a look at our newly created frame, then we can see that this column is added, but all of the entries are NaN, so not a number. That means the values themselves are missing. Now in order to retrieve a column from our data frame, there are 2 ways to do that. We can either use that dictionary-like notation where we provide the column name in brackets. In this case we would just get that column back, or we can use dot notation instead. So if we want to get back the year, we could type out frame2.year, and this will also give us back that specific column. Now we can not only retrieve the columns but also the rows by using the log attribute. So here for example we want to get back the second row, the row with index 1, and we can see those attributes displayed here. We can also modify the columns by assignment. So here for example we are setting the value for the dead column to 16.5, and if we now take a look at that we can see that for all of the different rows the value has been updated accordingly. Now we can of course also delete columns, and for that we are first going to add a new column to our frame2 data frame, which is going to check if the state is equal to Ohio, and then we'll assign a value of true or false. Now if we take a look at that, we can see we now have an additional column called Eastern. If we want to remove that column later on, we can use the del keyword and then specify the specific column that we want to remove. And this is going to delete the column. So if we have a look at frame 2 again, we can see that this column has been deleted. Now we could also create a new data frame from a nested set of dictionaries. So here, for example, rather than using a list as a key of a dictionary, we have a nested dictionary. And just as before, we can use that as a foundation for our data frame. So the same way we did that before, we would use DataFrame and then pass populations as an argument. And this, of course, is also going to create a new data frame for us. Now, if the values have a different length, as is the case here, for example, we have 3 key value pairs inside of our first dictionary, but we only have 2 key value pairs in our second dictionary. In such a case, the missing values will be declared as not a number. And there are a lot of different possible data inputs for our data frame constructor. So we could use NumPy's ND-array, for example, a dictionary of arrays, lists, or tuples, as we saw before, or for example, a dictionary of dictionaries. Now we can also make our data frames a little bit nicer by setting the name of the index as well as the name of the column. And if we now have a look at our data frame again, we can see that those values are added here. So the state and the year are then added to our data frame. We can also turn a data frame into an ND-array. For that we can call toNumPy on our data frame. And this is going to return a 2-dimensional array based on our data frame. And in this case here we had the same data type, float, for all of the different columns of our data frame. But of course this doesn't have to be the case. So if we look at our frame 2, for instance, we had different types, for example integer, a string, and floats. And if we go ahead and we call toNumPy on frame 2, we can see that the data type is updated accordingly. So in this case, it's updated to object to accommodate the different data types in our data frame. The third and final Panda data structure that we are going to look at are index objects. Pandas index objects are responsible for holding the access labels and other metadata. And any array or other sequence of labels that we use when we construct a series or a data frame is internally converted to an index. So let's look at an example, and we are going to create a new series object. And to do that, we are going to use the aRange method, which is part of NumPy, to create an array with the values from 0 up to but not including 3. And we specify the index to have the values a, b, and c. We can extract the index from our object by calling index on our object that we created and assigning it to a variable. So let's have a look at our index object. And we can see the index that we constructed, so with the values a, b, and c, and the data type, which is object. We can also use slicing if we want to look at just part of our index. So here, for instance, we are starting from index 1 all the way to the end, so we are excluding the first entry. Index objects are immutable, so if we try to change the index at position 1, for instance, to a different value, we're gonna get back an error, because our index does not support mutable operations. And unlike Python sets that we saw before, a pandas index can contain duplicate labels. So for instance, we could construct a new index, which has the values foo and bar included multiple times. And we can see this is also returned to us, so a label can be used multiple times. Here's an overview of some of the index methods and properties available to us. So for instance, we can use the append method to concatenate our index with additional index objects in order to produce a new index. We can also, for instance, delete elements from our index or check whether our index has no duplicate values by using the isUnique attribute. Now that we learned about the 3 different Panda data structure, let's continue with covering the essential functionality when working with Panda. The first method we are going to cover is reindexing, which allows us to create a new object with the values rearranged to align with a new index. So let's switch over to IPython and let's have a look at an example. We are going to create a new series object with 4 different values, and we are also going to specify an index with the values d, b, a, and c. Let's have a look at the object we just created. So here we can see our index displayed on the left side and right next to it the associated values. Now looking at this, we can see that it's out of order because we're not starting with a, then b, c, and d. To change that, we can use the reindex method, and we would call reindex on our object and then pass our new index to it. Now in this case, we have an additional value added, e, which does not exist in our original index. So in such a case, the associated value would be set to nan, so to not a value. So let's have a look at object 2 that we just created. And here we can see now it's displayed in the specified order in our index. starting from A, B, C, D, and then we have E. And again, we don't have a value for E, and therefore it's going to be displayed as NaN. Now for ordered data, like in a time series for instance, we may want to do some interpolation or filling of values when we perform our reindexing. And for that we can use the method option by specifying a certain method that we are going to use in order to fill the values. So let's have a look at an example. We're first going to start out again by creating a new series object, which contains several values and then an index that we specify. And if you look at our object, we can see our index here on the left and then the associated values. Now if we want to reindex this object, we can call reindex on our object that we created. And here we are using NumPy's arange method to create an array from 0 up to but not including 6. So the values are 0 through 5. And we are going to specify a method. In this case, the method is ffill, which forward fills the values. So if we look at the returned value, we can see now we have our index from 0 to 5. And by using ffill, the values for which no index existed are no longer NaN. Instead, they are forward filled. So basically we are using the same value as we had for the previous index value. So for instance, for index 0, we have the value blue. We didn't have index 1 before. So we are adding that using our reindex method, and we are going to use the same value again because we are using forward fill. So again, blue would be assigned. For index 2, we have a value of purple, so that's of course associated. We didn't have index 3, but now we're using forward fill, we are also going to assign the same value, and we repeat the same step for index 4 and 5, and the associated value, which is yellow. And there are additional function arguments that we can use with reindex. Here's a short overview. We can, for example, specify the columns. We saw the method argument before, which we used with ffill for forward fill. Alternatively, we could also use bfill, which stands for backwards fill. Or we could, for instance, use fill value, which allows us to substitute the value to use when introducing missing data by reindexing. Another essential functionality is the ability to drop entries from an axis. And for that, we can use the drop method. So let's have a look at an example in IPython. We're going to create a new object by using Pandas series data type, creating a range from 0.0 up to 4.0, and we're going to specify index A, B, C, D, and E. So if we look at our object, we can see that we have this data series created here, which is of type float64. Now if you want to remove some of the values, we can use the drop method. So as an example, we could drop the values at index C. So this would remove both the index and the associated value. And we can save the updated series object in a new variable, new object. So if we look at our new object, we can now see that A, B, D, and E and the associated values are still included, but the index and the value for C has been removed from our new object. We can also remove multiple values at once. So if we look at our object again and we want to make sure that we remove, for instance, both the values for C as well as for D, we can go ahead and use our drop method, and we can pass a list as an argument, including all the different indexes for which we want to remove both the index and the associated value. So in this case, D and C. Now if we go ahead, we can see we get back the remaining values of our series object. So the values at index A, B, and E, but the values at index C and D have been removed. Now when we work with a DataFrame object rather than a series object, we can delete index values from either axis. So let's have a look at an example. We are going to create a new DataFrame. We're going to use the range from 0 to 15. And then we have a number of different index values and columns that we specify. Let's have a look at our DataFrame that we just created. And we can see we have 4 different rows with different cities. And we have 4 different columns, 1, 2, 3, and 4. If we now want to delete some of the rows, we can specify the index for which we want to delete the row. So for instance, we can say that we are going to use our drop method, and we specify that we want to drop values with index Colorado and Ohio. So this is going to remove Colorado and Ohio as the rows here, and we just get back Utah and New York as the 2 remaining rows. If we instead want to go ahead and not delete the rows but the columns, we could use again the drop method, and instead of specifying the index, we are going to specify the column. So in this case, we want to remove column 2. so that we have 3 columns left and of course our 4 rows. Similar to NumPy array indexing, we can also use indexing with series. The only difference is that instead of only using integer values, we can also use the index values assigned to our series element. Let's have a look at an example and let's create a new series object by using the aRange method, and we're going to create 4 different entries. We're also going to assign an index with the values A, B, C and D. Now we can of course have a look at our series object and we can see we have those 4 index labels and then the associated values. Now just as with NumPy arrays, we can use an integer value to refer to a specific index. So for instance, if we want to have a look at the second element, the element with index 1, we can simply add that value inside of brackets and then we're going to get the associated value back. But additionally, we can also refer to the index value. So we could for instance say that we want to get the value at the index value B. So this gives us back the same value as using the integer index. We can also look at a range of values. So here for instance, we are taking a look at the value at index 2 all the way up to but not including index 4. So in this case we would get back the values for C as well as for D. And again we can use index values. In that case we would add the index values in brackets and then specify which values we want to get back. So in this case here we would get back the values for the value index B, A and D. Now while it's possible to return the values using this notation, the preferred way is to use the special log operator. So here we would call log on our object and then specify the different index values for which we want to get back the value. So this will give us back those same 3 values. And the reason we prefer the log operator is because of the different treatment of integers when indexing with brackets. To understand that better, let's have a look at an example. So we are first going to create object 1, which is going to be a series object with 3 different values. And we're going to use integer values as the index. And then we're going to create a second object, which is also a series object, but this time we're going to assign strings as the index values. So if we have a look at our object 1 and our object 2, we can see that for object 1 we have integers as index values and for object 2 we have strings as index values. Now if you refer to the values 0, 1, 2 inside of object 1, we're actually referring to the index values in this case. But if we do the same with object 2, then we get a result back that corresponds to the integer index. So therefore it's not really clear whether we're using the index values or the integer index. And to avoid that we would use the log operator. So if we call log on object 1, again with the values 0, 1 and 2, we're gonna get back the same result because we're referring to the index values. But if you're trying to do the same with object 2, we're actually going to get an error instead, because inside of object 2 we don't have any index values with the value 0, 1 and 2. So we always know what we refer to. Now instead of using the log operator, there's also the ilog operator. And whereas the log operator always refers to the index values, the ilog operator always refers to the integer index. So therefore if we call ilog on object 1, with the values 0, 1 and 2, we're referring to the integer index, and therefore we're always going to get back the first 3 values. And if we call ilog on object 2 with those 3 values, we also get back the first 3 values of object 2. Now we can of course also index into DataFrame objects, not just series objects. So for an example, let's create a new DataFrame. We're going to have a total of 16 values, and we're going to create a 4x4 matrix with the index being set to 4 different states, and then columns set to 1, 2, 3 and 4. So if we look at our data, we can see we created this table. And if we want to display individual columns, we can simply use the bracket notation and refer to the respective column, for example 2. And then we're going to get back exactly that column. We can also refer to specific rows by using an integer index. So here we're starting at index 0 all the way up to but not including index 2. So we would get back the first 2 rows of our data frame. But we can also use the log operator to display certain columns or rows. So for instance, we can call log on our data frame and pass our row name inside of brackets. And this is going to return exactly the values associated with the specified row that we selected. In a similar way, we can return multiple rows by simply using our log operator and specifying the row name. And this way we get back, in this case, the rows for Colorado and for New York. Of course, we can also use the ilog operator if we want to use the integer index instead. So we could, for example, call ilog on data with a value of 2 in order to return the values at index 2. So this would return the values in the third row here, so index 2. And of course, we could also return values for multiple rows, for instance, values at index 2 and index 1. So this would return the value for index 2, this is the third row here, Utah, and the values at index 1, so here our second row. And there are a number of additional indexing operations available with data frames. We looked at the log operator and the ilog operator, and we also covered that we can simply specify the column name in brackets in order to get back that specific value, either by specifying a single column name or multiple column names. While there are a lot of parallels between Pandas objects and regular Python objects, there are also some important differences that we need to understand. And for an example, let's switch into our terminal and let's first create a new series object with 3 different values using the arange method. And if you have a look at that, we can see we have the values from 0.0 all the way up to 2.0, and we have our default index 0, 1 and 2 added. Now we know that when we work with regular Python lists or tuples, we can specify the index in order to get a certain element back, and we can provide positive values, but also negative values if we want to start from the end of our list or tuple. But if we try the same with our Panda series, so here we are referring to the value -1, trying to get back the third data entry point, we're actually going to get back an error message. And the reason for that error is that we're using the default index values 0, 1 and 2, and Pandas is not able to associate a value with the index value -1. Now if we are using a non-integer index, for instance if we are specifying the index to be A, B and C, so that our second series object looks like this, then we would be able to refer to a value by its integer index, so in this case -1. And this is not going to throw an error, but instead give us back the last element inside of our series object. Now Pandas can also make it a lot simpler to work with objects that have different indexes. So for instance, when we add objects, if any index pairs are not the same, the respective index in the result will be the union of the index pairs. So for an example, let's create 2 different series objects. The first one, S1, is going to have 4 different float values and a value index corresponding to the strings A, C, D and E. And we're going to create a second series object with 5 different values corresponding to the value index A, C, E, F and G. So if we have a look at S1, we can see we have 4 different values, and in S2 we have 5 different values. If we now add S1 and S2 together, we can see that if the value index is the same between both series objects, the values are being added together. But for the label locations that do not overlap, so in this case for D, F and G, it's creating missing values. And the same happens with data frames. So here we are going to create a data frame with 3 rows and 3 columns, and a second data frame with 4 rows and 3 columns. So if we have a look at those 2 different data frames, we can see that the dimensions don't match. So if we now go ahead and we add our first data frame and our second data frame together, then we can see we get back a lot of missing values because the rows and the columns do not match. So for instance, only in the case of Ohio and Texas, we would get back values. And that's because in our 2 data frames, those are the only 2 states that are included in both of our data frames. And even on those rows, we have some missing values for the columns C and E, because those are the columns that are not included in both of the data frames. So C is only included in the first data frame and E is only included in the second one. The element-wise array methods, which we covered for NumPy in the last video, also works with Panda objects. So if we look at an example, we are creating a new data frame here, and we are using NumPy's standard normal method, which is part of the random module, to create random values in a data frame with 4 rows and 3 values. So if we look at our data frame, we can see that we have 4 different rows, 3 different columns, and random values generated. And we can use other element-wise array methods. For instance, we can take the absolute value of our frame, and with that we get back our data frame, but only with positive values. Now quite often we also need to sort a dataset based on some criteria. And for that we can use the sort index method. So let's say we have a series object here with 4 different values. And in our case here we have a value index that is not in order, so D, A, B, C. But if we want to sort our index easily, we can simply call the sort index method on our object. And this is going to reorder the values in our series object and sort it based on our value index. Now if we have a data frame instead, we can sort based on either axis. So here we have a data frame with 2 rows and 4 columns. And if we look at our data frame, we can see it's again out of order. So both the rows as well as the columns are out of order. And if we want to sort the rows, we can use the sort index method again. And this is going to sort based on our columns and reorder it to 1 and then 3. If we want to sort by the columns instead, we can use the sort index method again, but then we need to provide the axis argument and set it to columns. And this way we are reordering our data frame, but this time it's sorted based on the columns. And by default we are sorting based on ascending order, but we can of course also change that. So if we want to sort our columns in descending order, we would set ascending to false. So in this case we start from the back. So here our columns are sorted in descending order, starting from D, then C, then B, and finally A. So up until now, most of the examples that we looked at had unique access labels. And while for many of Pandas functions like reindex, it's required that the labels are unique, that's not mandatory. So let's have a look at an example and let's create a new series object that has 5 different values and has index values that are not unique. So we can see that the values for A as well as for B are repeating. So if we look at our series object, we can indeed see that the index value is repeating for both A and B. Now in order to find out whether the labels are unique, we can use the isUnique property, which is part of the index attribute. And this way we get back false in this case, because our index is not unique since we have repeating values. Now if we are working with those kind of duplicates and we are referring to an index value, so for instance if we want to get back the value at the index value A, we would get back 2 values in our case because our series object contains 2 index values or labels with a value of A. And the same logic of course also applies not only to series objects but also to data frame objects. So if we create a new data frame with 5 rows and 3 columns and repeating index values just as before, we can first have a look at our data frame and see that our index values are indeed repeating. And if we now use the log operator to have a look at the rows with, for instance, the index value of B, similar to series objects, you would get back 2 rows since we have 2 rows with the same label. So to summarize, Pandas objects are equipped with a set of common mathematical and statistical methods. And typically we would focus on extracting a single value such as a sum or the mean from a series, or a series of values from the rows or columns of a data frame. So if we have a data frame, we can have a look at it. We have 4 different rows and 2 different columns. We can call the sum method in order to sum up the values of our columns. So in this case, we would get the sum of the columns 1 and 2. And of course, our data type is of type float64. If we want to sum based on the rows instead of the columns, all we need to do is to use our sum method and pass the attribute axis to it and set it to the value of columns. So in this case, we get back our different rows from A to D, and we're summing up the values in our columns. So for B, for instance, we create the sum of 7.1 and minus 4.5, so we get back 2.6. Now instead of creating the sum, we can also, for instance, get back the maximum value of a column. For this we would call idxmax on our data frame, and in this case we would get back the maximum value for the first column. If we have a look at the first column here, we can see that the maximum value is 7.1, which corresponds to row B. So this is what's returned in the first line here. And then for our second column, we can see that the largest value is minus 1.3, which corresponds to D. And therefore, in the second line, we get back 2 and D. And in a similar way, we could, of course, also have a look at the minimum value. So for this, we would call idxmin. And this is going to give us back the minimum value for the respective columns. So 1 and D and 2 and B. Now, if we want to create multiple summary statistics in one step, we can use the describe method. So if we call that on our data frame here, we're going to get back a number of different statistical values. And So for instance, we get back the count, so the number of actual values, which for column 1 are 3 different values, and for column 2 are 2 different values. We get the mean of the value, the standard deviation, the minimum, and then the different percentiles. And we have a number of different descriptive and summary statistics methods that we can work with. So we saw describe before, we saw IDX min and IDX max, we saw the sum before, and we have additional options to get back the mean value, the median value, as well as for instance the product of all values. We can also calculate correlation and covariance, which is computed based on pairs of arguments. So in order to look at an example, let's head over to GitHub, to the book's resources. The link is also in the description down below. And here we can go ahead and we can download some example data by downloading the repository as a zip file. Now once we downloaded and extracted the zip file, we can see that we have 2 different folders, dataset and examples. And we can copy the examples folder into the directory where we are working from. So this could, for example, be your username. And if we then switch over to IPython, we can call pandas readPickle method. And we're going to provide the path to the file we want to look at. So inside of the examples folder, there's a file called yahoo_price, which we can also see over here. And we're basically reading this file and saving the values inside of price. We also have a second file inside of our examples folder called Yahoo volume. And this also includes financial data that has been extracted from Yahoo. And we're going to store that value inside of volume. Now we can use pandas to calculate the % price change, which is something we're going to cover in more detail in a later video. And specifically, we are going to call the % change method on our price that we read out before, and we're going to save the values inside of returns. If you want to now have a look at the last couple of lines, we can use the tail method on returns, and this is going to give us back the last 5 values, and this is going to give us back the % price change for a couple of different stocks. So here for Apple, Google, IBM, and Microsoft. Based on that dataset, we can also calculate the correlation. So for instance, we can have a look how the returns of Microsoft correlate with the returns of IBM. So in this case, we have a correlation of almost 0.5. And similar to the correlation, we can also calculate the covariance. So here we are calculating the covariance between Microsoft and IBM. And if you want to see the full correlation or covariance matrix, we can use the core method for the correlation. So here we can see how strong the different stocks correlate to each other. Of course, along the diagonal axis, the value is always 1, because each stock correlates with itself with a value of 1. But then we can also have a look how strongly Google and Apple, for example, correlate, or IBM and Microsoft, for instance. And in a similar way, there's also the COV method to calculate the covariance between the different stocks. And we can also compute pairwise correlations. So for example, here we are calculating the correlation with IBM. And we're getting back how strong the price changes of the different stocks are correlated with IBM. And again, we're going to cover all of that in more detail in a future video. We also have a number of different methods we can use with pandas in order to calculate unique values, value counts, and memberships. So for an example, let's create a new series object which has a number of duplicate entries. So we can see, for instance, that the value A is added multiple times, as well as the value for B and C. And we can now use the unique function in order to remove all duplicates and only get back the unique values. And that return value is going to be saved inside of our uniques variable. So if you now have a look at uniques, we can see we have an array here of different values, and each of those values is a unique value. So we removed all the duplicates. We can also count the number of values by using the value counts method. And this is going to count how often each of the values occurs. So in this case here, C occurs a total of 3 times. Same for A, B occurs twice, and D only occurs a single time. And of course, we have a number of different methods available. In addition to the unique method we just saw, we can, for example, use the isIn method to compute whether a certain value is contained inside of a series or DataFrame object. We covered the basics of pandas and learned about the essential functionality. In the next video, we're going to learn how we can read and write datasets using pandas. In order to not miss any videos, feel free to subscribe to the channel, and see you guys in the next video.